this video, I'll be working through question 5 of the 2017 Scholarship Physics exam. Question 5, the ramp projectile. A spring-loaded plunger launches a ball at speed v0 from the corner of a smooth flat board that is tilted at an angle thigh in order to make the ball hit a small target at the adjacent corner at a distance d away, shown in the diagram. The ball can be considered sliding without friction. Assume angle theta is required to hit the target is unknown. Show that the maximum distance up the board is given by delta y, which is how far up the board it is, equals half v0 sine theta squared divided by g sine thigh. So what are we going to do? So we're going to write down what we have and what we're trying to find. So can we see that? Yep, at the top, the top, and we're just looking at what would be, I suppose, if you tilted this table round so it's vertical, you'd have a vertical component and a horizontal component, but this is pretty much just projectile motion with decreased gravity, if that makes any sense, because now gravity is, there's only a small component of gravity acting, because obviously it's on an angle, and we'll get to that soon. In fact, we'll do that now actually. So remember I said the trick to finding sort of what the component of gravity is the largest can ever be is 9.8, so that's the acceleration, 9.81, which means we have a triangle that looks a little bit like this, the right angle being here. This angle here, where is it? This angle here is thigh. That is that angle here, thigh. That angle here. And if gravity is acting downwards, and we translate this across, I'm going to leave that, but you can sort of just memorize it. This always is the hypotenuse. This here is the angle thigh, which means we'll cross it out. We'll make that G, which is 9.81. In other words, this is the hypotenuse. This is the adjacent, so this would be G cos thigh, and this would be G sine thigh. And we can already see that we're going to be using G sine thigh, but if you look on the table, you can see that's down the ramp. This here's down the ramp, so you're going to be using G sine thigh. So we can write out. We'll put it over here. We'll put it over here. G equals G sine. Missing an N, thigh. It's a bit ambiguous, but whatever, we'll just leave that there. So at the top, the final velocity is going to be equal to 0, just like you throw a ball up, it stops at the top and then comes back down. The initial velocity, well, we need to figure that out. So we have v0 going up like that. We have the two components, the horizontal, that's a weird triangle, the horizontal and the vertical component. We're looking for the vertical component, so we have v0. This is theta, so in other words, this is the opposite, that's our hypotenuse. We've got v0 sine theta, and I'll chuck in this here, this is v0 cos theta for the horizontal component, because we're probably going to need that later. So in other words, the velocity initial is going to be v0 sine theta, and the change in distance, we'll leave that there. So now we have initial velocity, final velocity, the acceleration, and we're trying to find the distance. So the only formula that have, which is it's from level 2 physics, is Vf squared equals, because you don't have time, Vi squared plus 2AD. And now all we do is we simply substitute in and rearrange. There's no final velocity, so we can just cross that out. In other words, minus Vi squared divided by 2A equals D. In other words, we have V0 sine theta squared, put brackets around that, divided by 2G sine thigh equals the height, which is delta y. There we go. And there's a minus here, but gravity acts downwards, so that minus cancels with the minus of gravity, so it all just becomes positive. Right, by considering the horizontal motion, show that the time to reach the target, t, is given by time equals distance over, or d over, which is d is that one there, over v naught cos theta. This is easy. This is just, distance equals velocity times time. In other words, time is equal to the velocity over the distance. No, wait, hold on. No, the distance over the velocity, which is equal to literally just the distance here across. So we got d over the horizontal component, and the horizontal component is v naught cos theta. We figured that out there. V naught cos theta is v naught cos theta is the horizontal component. Horizontal component. That's pretty straightforward. Like I said, we were going to need it eventually, and we do now. Derive a relationship for the time to reach the maximum height delta y. Express your answer in terms of v naught, theta, and phi. So we'll just start off with, we have the time. So this is the time from one side of the board to the other side of the board. So half of that is going to give us the time to the top, which is just sort of an extrapolation of year 12 kinematics, projectile motion. Right, so you're going to be using Vf equals Vi plus At. In other words, at the top, you're going to have no final velocity. So 0 equals your initial velocity. This is your vertical velocity, equals V naught sine theta, which is right there. This is your vertical velocity plus, and now we're going to have G. Do we need to use all that there? No, we're just trying to rearrange for time. So there we can just go G sine phi time, and we could substitute that in, but then we wouldn't be rearranging for time. So what we do is just rearrange this for time. So we move this over to the far side, and then we move that underneath, and we just get V naught sine theta divided by G sine phi. And this would have been a minus, but because gravity acts downwards, that's a minus as well, so they just cancel out, so we just get equals to time. Very straightforward. Right. Show that the angle theta at which the ball should be launched, so that the target is reached, is theta equals half sine inverse G d sine theta divided by V naught squared. So this is just going to be a little bit of rearrangement and a little bit of algebra. So what are we going to do? So first of all, we've got change in time, or time should really be equal to d over V naught cos theta from the previous page, but it's also equal to what we just solved just before, V naught sine theta over G sine phi. Why am I doing this? I'm doing this because I'm looking at that and it's got no time in it, but it's got everything else except for delta y. And these don't have delta y in it. So basically, I want to use this expression to solve for that, or to get to there, knowing that I'm not going to have time in it, and knowing that the time occurs the same. So like as time moves forward, it's going to be moving up, and it's also going to be moving sideways, horizontal, and the vertical components add together to create the motion. So basically, I'm just making that happen here. So we will move the G sine theta over on one side and the V naught cos theta onto the other side. So we get, write that here, d G sine phi is equal to, what do we got? 2, hold on. There we go. Yeah, I know what I did. This, we need to double this, times that by 2, because this is the time to get to the top. We want the time to get to the top and the bottom, because that's when, this here is the time to get all the way across. This here needs to be doubled to get to the top and to the bottom. That's what I missed out. So it's going to be 2, what is it, V naught sine theta V naught cos theta, and look at that, they gave us this equation because we're going to have to use it, and we're going to use this one here now. So we're going to substitute, we're going to use this here, we're going to swap this out, so we're going to have dg sine phi is equal to V naught squared 2, I'll fully do it, 2 sine theta cos theta, which is equal to V naught squared sine 2 theta. There we go. And now all we're trying to do is rearrange for theta. So we've got dg sine, it's very messy, phi divided by V naught squared is equal to sine 2 theta. In other words, theta is equal to GD, what did I go, I did that backwards, sine phi divided by 2 V naught. Is it 2? No, it's not. I need to take the inverse. That's just V naught squared, and then I take the sine inverse of this, which brackets around that, and then I'll divide, well, times by half. There we go. And that's the same as that. That's good. Sweet. Next question. Now we consider the case where the ball rolls without slipping. If the ball with mass m and radius r has rotational inertia 2/5 mr squared, and assuming again that theta is known, show by considering conservation of energy that delta y equals 7/10 V naught sine theta over g sine theta. Looky, that is exactly the same formula as this one here, except for the fractions are different. And the fractions are different because rolling stuff has more energy, because it starts off with rolling energy and like moving energy. So we'll start off with this. What are we going to do? E k, the translational energy, plus, it starts off, well, it's assuming it's rolling to begin with, so it's going to have rolling energy at the bottom. E k r o t, rotational, is going to be equal to, and this is the energy at the top, so this is like the potential it's going to, yeah, so this is the top of the, how high it's going to go. So at the top it's going to have mgh, gravitational potential energy, plus still rotational but less because it's not spinning as fast because it's only got the horizontal component now, plus EKT, which is a horizontal component. This is just like the initial component, so we're going to expand this out. There's going to be half mv naught squared, because this is half mv squared, and this is just the initial energy. This is why it's kind of easy to use energy to solve problems, because you don't need to do like components or anything. Energy is just a scalar product, so you don't need to like break up the vectors. Plus the rotational energy is going to be, what's going to be? It's half I omega squared. I'm going to chuck that up here. E k r o t is equal to half I omega squared. In other words, it's going to be equal to half 2/5, which is the same as 2/10, because when I times that half, I want to times 2/5 mr squared by 2/10, so it's going to be by a half. 2/5 times a half is 2/10. 2/10 mr squared, that's the inertia, times omega squared, is going to be equal to mgh. I should have probably swapped out h for delta y. No, we'll do that next. Plus 2 over 10 m squared. I'm just literally using the same thing as I had there. M squared omega squared, because I've already rearranged that for that. Plus the translational energy. So at the top it only has the horizontal component of velocity. So it's going to be m. What is the horizontal component? The horizontal component of velocity is, what is it? V naught cos theta. Yeah, there we go. V naught cos theta, and that's v squared. There we go. Right. Now what are we going to do? Right, we are going to write this out, and we'll span things out, and we'll try and cancel some stuff off if we can. Probably we will be able to. It's got half m v naught squared plus 2 over 10 m r squared. And now what we're going to do is, so omega, or the angular velocity, we'll swap that out for the regular velocity. So v equals r omega. In other words, v over r is equal to omega. So that's going to give us v squared over r squared. Oh, look at that. We can cancel those r's just like that. And this is v naught squared, because this is just the initial velocity rotating. Because it happens that the translational and rotational velocity are the same if it's not slipping. Hopefully it's not slipping. Mg, right, the height. How high is it off the ground? It's certainly not y off the ground. It's going to be delta y, because that's that thing there. We want to find this component here. So like how high if you just fall through the table. So that's going to be, we've got the hypotenuse, we're trying to find the opposite, and we've got thigh, so it's going to be sine. So we're going to have, that's the hypotenuse, sine thigh. If you need to prove that to yourself, you're more than welcome to. Plus, same again, 2 over 10, which is just that half times that 2/5. M r squared, and now we had v naught squared over here, but this is just the horizontal velocity, and the horizontal velocity is v naught cos theta. So that's going to be bracket v naught cos theta bracket squared over r squared. Oosh, this is going to get real messy soon. Plus half m, what is it? V naught squared cos squared theta. Right, now we're going to cancel a whole lot of stuff. So we're going to get rid of the masses, because every single term has a mass in it. So we can cancel out all the masses. We are going to, I'll write it out again, and hopefully it's not too crazy messy. V naught squared over 2 plus, what is this going to be? 2v naught squared over 10. Hope you can see that. Is going to be equal to, we'll go g delta y sine thigh plus, what are we going to do here? So we cancelled out those, we can cancel out these r's as well, so it's going to be 2 over 10 v naught squared cos squared theta plus, what are we going to have here? Half v naught cos squared squared theta. Whoosh, there we go. Now what we're going to do is we're going to add these two together, because this is just a fraction. So we are going to have 7 over 10, yeah, 5 over 10 plus 2, yeah, 7 over 10 v naught squared, yep, is going to be equal to delta y, I swapped the g around because I'm an idiot, sine thigh plus, we can add these two together as well, so that's going to give us 7 over 10 v naught squared cos squared theta. And now, what should we do then? We will move this over to the far side. So we're going to move this over to the far side, so we get left with this here. So we're going to have, we've got two 7/10s and two V0s. This is going to be there'll be some little algebra trick that'll just happen with us. So V0 squared 1 minus cos squared theta is going to be equal to delta y g sine phi. I moved this over here and I pulled out a common factor. So if I expand this out, I just get this times this, and it's going to be minus 1 minus cos squared theta. If you rearrange this here, if you move the cos to that side, so 1 minus cos squared theta gives you sine squared theta. Oh, look at that, we're using what they've given us. So that is going to be equal to 7/10 V0 squared sine squared theta. In other words, she's running out of space. Delta y is equal to 7/10 V0 sine theta squared, we'll write out how they've given it to us, over g sine phi. Assuming no energy is lost. Assuming, how do I spell assuming? No energy is lost. No energy lost. Right. Consider the situation when phi equals 0. So I'm going to pause it, write the answer, and then go over it. Right, I've said there's no radical component, so it's just going to roll off the table. It's pretty straightforward. If the table's flat, it's just going to go straight off the table. Simple. Right, comparing the answers for this one here to this one here. Why is the answer for C larger? So I'll pause it, write the answer, then discuss. So I said in C, the ball started with more energy in the form of EK rotational, so kinetic rotational energy. The vertical component of this is transformed into gravitational energy, so it rolls higher up.